You remember, when we did this last time? This was. Escape. Height above ground. Or object. From. Up. Or down. At speed. V0. And height. Yes. Remember how we brought that last time? Remember how we did that, you know, I said I'm on a building, I throw a rock. You remember how, did you understand all of that? Okay, so when I say thrown up or down, if my velocity is, negative, then I'm throwing it down. If V0 is negative, I'm throwing it down, V0 is positive. So this is exactly what's going on in this example. It says neglecting air resistance, the motion of an object moving vertically near the Earth's surface is determined by acceleration due to gravity, which is approximately 9.8 meters per second squared. So what they're saying is, suppose a stone is thrown vertically upward at t equals 0 with a velocity of 40 meters per second on the edge of a cliff that is 100 meters above a river. So in this case, that's how fast you check it up, right? And S0 is 100. That's how far above the surface of the river you are. So you're standing on the cliff, looking down the river, locked up. So this is just this equation, it's numbers. It said, so what does it ask? Find the velocity of the object from t greater than 0. Well, the velocity right when you throw it is this. We derived this last time, and part of what we got along the way was velocity should be the derivative of this, which is, I guess, minus gt plus v0. We're sort of doing this in reverse. Last time we derived this using antiderivative, we started at g and we got gt plus s0 and so forth. So what the book should say, I guess, is minus 9.8 plus 40. Right? Because their version of, and that's what we got. Their version of G is minus 9.8. 40. I like our equation better because our equation works on the moon, it works on Jupiter or whatever. You just have to find the appropriate thing. So there's velocity. Or these find the position of the object for t greater than 0. Well, they're sort of going backwards. They're doing what we did yesterday. So the S T for us should be minus 4.9 squared plus 40 t plus 100. See if we agree with them there. Looks like we do. Is that okay? Right, just plugging in G and V0 and S0 that. Find the maximum height of the object above the river. Okay. How are we going to do that? The maximum height should be at what units? Yeah, 6 feet. You're right. It's meters in this one. So I'm gonna have to use this equation. But the question is, to use this equation, I've got to plug in some time. How do I find the time? That's right. When does this thing reach its maximum height? Well, at its maximum height, what can you say about its velocity? Yeah, it's zero because it goes up right before it turns around, it's got velocity zero. So we need a time to make this work. That's sort of the turnaround point where the velocity zero, it hits the apex of its travels in each direction. Right? So we get minus t plus 40 is equal to zero. And so I get t is 40 over 9.8. So it should be just like a little bit bigger than 4 seconds. And I'm sure that he gave you this. Right. And so this is the turnaround point. So the maximum height is S S minus 4.9 40 over plus 40 whatever that number is. Just plug that in, go for it. And that's, I guess they came up with about 100. Is that clear? Am I addressing these questions you were asking? Okay, so part D says, with what speed does the object strike the river? Right? Okay. Okay. What equation are we going to use? What's the ninth equation that's going to barf out speed for us? So yeah, so the equation we're going to need to use to tell us the answer that we want is this one right here. Because this is the equation that tells us what velocity is. We've got the same problem that we had before, but what do we need? We need a time to plug in. How do we get the time? What's that now? There you go. T is minus 9.8 equals 40. Appropriate. How do we find that? Well, the important piece of information here is the fact that that thing hits the river. All right, so you have to solve this equation to get yourself. So what do I get here? So I don't use myself 4.9 squared minus 40t minus 100 0. I'll just change the sign of that. quadratic formula that t is equal to 40 plus or minus the square root of this square, which is 1600, and that's going to be 400 times 4.9, right, which is 6. Yeah. So over 9.8. So I get 40 plus or minus the square root of 3560 over. Now, the square root of 3560 is more or less, well, it's the neighborhood of 60, I guess. So it's 59.66, say 59.67. Now, which this actually gives me two solutions, right? Which one is germane? Which one? The positive, why the positive one? If you use the negative, if you use the negative one, you actually get a negative number on the top because 59 is bigger than 40, right? And so that's actually before we start the clock, right? So it doesn't, it's not germane. So, what do I get? More or less what I get is the 40 plus 59.67 over 9. Yeah, 9.8, which is approximately equal to, that's what 99.9.8. So it's a little bit, just a smidge bigger than 10 is. Oh, but right. So I chuck this rock up in the air, it hits the river in 10.2 seconds. Now, what the question is, how fast is it going? It smacks the surface of the river. So we need this velocity equation, which is this one. That's 9.8, 10.2 plus 40. So this comes up to be I get about minus 59.96. And that should be a meter. So yeah, it's pretty healthy. So what is the negative on that answer signify? Yeah. Okay, any questions on that? Okay, let me give you all, I want to talk about the quiz from yesterday. But first, let me give you a new, I want you all to work through this example. Okay, this is kind of a silly example, and I'll show you why. Use Newton's method. to approximate. Root. And for this one, I do mean the root, because there's only one root. This function will have one root. F of x equals x. So you can use a calculator. Now, can you explain to me why this has been a sole problem? Why you probably wouldn't use Newton's method on this? Anybody know what this function looks like, by the way? Cube root of x. Well, so do you know what x cubed looks like? See a picture of that, right? X cubed. Now imagine it's split around the line like that. Yes. Now, tell me why you probably would use Newton's method to approximate this root. It's just zero. However, there is something important that this example illustrates. I want you to start with, let's just make it easy, start with x equals 1. And x 0. I want you to use start with x 1 and use Newton's method. Find x1 and x from the next and then the next. And then I want us to observe kind of what happens here. Okay, so we've gotten, start with an initial approximation 1, flashes over to -2, and then its next stop all the way over here at 4. Anybody identify what the problem is if we're going to use Newton's method to approximate the root of this function? What happens to successive approximations? Which is a better approximation of the root? First one we picked or this one? Yeah, because you've actually got further away, right? You're only 1 away here. Now you're 2 away. Now you're 4 away. Right? Notice the curvature of this pushes the approximations out. This is another thing that can go wrong in Newton's method, right? But in this case, it'll be fairly obvious that what happens is your approximations push further away, and it's obviously not converges. But this is yet something else that happens. So you see what happens, right? Because if you notice, the tangent line lies over this. This is vertical tangent. So this actually pushes it farther away than the root. This makes it worse. So forth. Okay. Okay. Any questions? So that's another hazard. This is the kind of thing that I want you to be able to think about and understand a little bit. And this brings me to, last quiz. So, I want to kind of go over this. I had a problem on the quiz that said this. Consider, so I'll let the problem out, glory. Y x squared. Four. Points. Five. Closest. Point with points. To, uh, a 0, 1/2. What we're trying to do is find the closest point parabola. Okay, so let me illustrate this for you. Here's y equals x squared. And I give you 3 points. I give you 1/2, 0, 1/2, 0, 1. And down line here. And I asked you to find the point or points on the parabola that are closest. How many answers do you expect to get for, oh, and let me emphasize, the vast majority of you all tried something new, but this has nothing to do with you at all. This is an optimization problem. How many answers do you expect to get for this point right here? How many points do you suppose are minimal distance? I would expect there to be one, right? So if you imagine this is from there, it's probably somewhere along in here, right? This closest. What about this one? That's a little harder to tell, right? It looks like maybe here, or maybe there's a close point here and here too. It's hard to tell. Same problem with this, maybe here, maybe some more, I'm not sure. So I think these two might be a little bit more hard to discern. This sounds really obnoxious, right? This is like 3 problems. Find this, and this. Let me tell you the best way to do this kind of thing is don't use the specific points until you absolutely have to. Right. So the best advice I can give you is do this generally. Only use specific points where convenient for you. This will save a lot of play there. So here's what I'm going to do. And I'm also going to give you more of this advice here. I'm going to draw a point AB here. And I'm gonna kind of use this picture to set up what I need. What I'm doing in all these problems is I'm trying to minimize the distance, right? And I did draw this outside of the parabola, and that's just for my eyes. It's not gonna matter, right? The equations, the math will tell you everything. The equations are blind. This is just helping me because I'm weak-minded. This is the point x squared. That makes it a little bit easier, right? Because whatever the x coordinate is, y coordinate is x squared. Because this point is constrained to be on this graph. Everybody okay? Now, what I need to do is I need to compute the distance between these two, right? I seem to remember the distance formula. Basically, distance formula, there's no mystery to it. It's daggers and stick up umbrella. If I have, so let me give you a blast from the past here. If I have x0 and y0 and x1 and y1, and I want to know the distance between here, the distance is the square root of x0 minus x1 squared plus y0 minus y1. And really, what you're doing is you're just taking this triangle here, which is x0 minus x1. That's what that length is. And this one right here is, well, actually, let me write this right here. Actually, this one's y1 minus y0 in this coordinate system, and this one is x0 minus x1, but it doesn't matter. Take the difference and square it. Right? So basically, what you're doing to find this distance is take the square root of this plus the square root of this, take the square root of this. Pythagoras is there. Okay, so I need the distance between this and this. Now, one thing that really is obnoxious is the fact that the distance is the square root. And I know that this is a calculus class and I'm gonna have to take a derivative at one point. And I don't like taking derivatives of square roots, right? Because you get those obnoxious powers -1/2, and you also have to do the chain rule. You have to multiply by the derivative of what's inside. Do I agree with that? So you don't have to do this, but I'm making my life easier by doing. Let's just minimize the square of the distance. So the idea behind this is to make the distance as small as possible. Just make the crap that's under the square root as small as possible, and that'll do the trick for you. And that'll save you a chain rule. Everybody understand? So if you want to make the square root of a positive number as small as possible, just make that positive number small. Everybody okay with that? This will make my life a little bit easier. So let me write the square of the distance here. This is x squared minus b squared plus x minus a squared. I want to minimize this. Because actually, if you look back at the question, it doesn't even ask what the distance is. It asks what's the point that's closest. So I don't even have to tell the distance, I just have to tell the number. And even if I had to tell the distance, I'll just take a look. This is the square root of it. Okay. X is my variable. That's what can change because I'm moving this dot along the parabola trying to find the closest point to along the parabola at this point. It's off the parabola. So X can vary. A and B, even though I haven't specified them, are constants, right? This point doesn't move, right? I'm going to later plug in 3-0 for AB and then this and this, but I guess I need to know what my playground is. What values for extra program is problem? I don't think there's any reason why we have to start at 0. In fact, I think I've got freedom to run all of this around, so it's any value. Anything goes. And that makes me a little bit sad because at the end of the day, what I'm gonna have to do is I'm gonna have to, it's not a continuous function closed interval. I just can't plug in the endpoints and check out. Figure it out. Okay. Let's take the derivative. And remember, A and B are constants. So let's do this. The derivative of this is 2 x squared minus b times the derivative of the side, which is 2x plus 2 x minus a. I'm going to clean this up a little bit. This is going to be 4. That's going to be 4x times this, which is 4x cubed. 4x times this is minus 4bx plus 2x minus 2a. Yes? So s prime is equal to 4x cubed plus 2 minus 4bx. I don't want to lose anybody, so any questions? Difference in the height of y's, x squared minus b quantity squared. So good here. Difference in the x squared, quantity squared. Okay, so that's just y. Right, y. This y coordinate minus this y coordinate squared. This x coordinate minus this x coordinate squared. Thank you. Are you saying that this is a square and so like x squared plus size, right? It's like square root of like well, so I'm not completely understanding your question because there's no square root here. You mean from over here? Yeah. Okay. You square root both sides. Then I'll just keep like beats. So d squared is this. Okay. I just call this S because this is just an object, right? This is just something. I want to make this as small as possible. Notice that this thing right here can never be negative, right? Because it's some two squares. Smallest can never be zero, right? And so I've just made my life a little bit convenient because instead of this more complicated thing, I'm like, you know what? I'm not going to minimize this whole thing in the square root. It's complicating my thing, making me do chain rules on taking the derivative. I'm just going to make what's inside the parentheses as small as possible, and that should make the distance as small as possible. Right? It's just a shortcut. So technically, I'm doing a different problem here, but it will give the same answer. Did I clear that up? But are you okay? Okay, so I think this kind of, does everybody understand how I got the derivative? Took the chain rule and multiplied it. Okay, this is the time when it becomes convenient to do the numbers. So let's go through. This is kind of as far as I'm taking it. So A. This is the one that I was for sure there should only be one answer to. So in this case, I have A is equal to 3, B is equal to 0. Right? So my function here, S is equal to x squared minus 0 squared. So plus x minus 3, which is x4 plus x minus 3. Right. And my derivative, again, I'm going to put in the AB business. Let's see what was B was 0. So this is 4x cubed plus 2x minus 0. 4x cubed plus 2x minus 6. Let me see if I can make this a little bit just pull 2 out of that. Now, here's the thing, look at the critical numbers, right? This was sort of the hardest one to actually find critical, because this is a cubic. But again, does anybody see a number I can plug in for X that will give 0? Think of a value X that you can plug in for that. And it will be good. Everybody agree with that? So I put in 1 for this. This will be a critical number. And that's enough of a clue. This factors, it has to have a factor of x minus 1. Why is that? Because when I plugged in 1 at 0, this has to have a factor of x minus 1. And so now I can just divide out and figure out what's left over. If this is 2x cubed, this better be 2x squared minus 2x squared, so that's plus 2x, and that better be 3. And if you multiply this back, you get 2x cubed minus 2x squared minus 2x squared minus 0. Oh, 2x cubed, 2x squared minus 2x squared, 0. That's going to be 3x minus 2x is x minus x equals 1 is a critical number. No critical numbers come out of this. How do you know? Well, you use the quadratic formula. Y'all remember the quadratic formula, right? What's the crap that goes under the radical in the quadratic formula? This squared minus 4 times this times this. Agreed? I don't know much, but this squared is 4 minus 4 times 2 times 3. That's negative. No solution for this. Right? Okay with that? So x equals 1 only critical number. So let's look at the derivative here. You've got one critical number at 1. What's true about the sign SIGN of the derivative? Well, if you are to the left of 1, something like 0, you're negative. And if you're to the right of 1, something huge, you're positive. So what happens? Go down, go up. This is a local min. And it's also an absolute min. Because you go down and hit it, and then you go up forever. So this is as close as it gets. I get what? I get this thing right here, the sign?
Yes, sir.
Okay, yes. For example, all you need to do is plug in something to the left of one, say 0, and that gives me -6. And to the right of 0, something like 2. Well, actually, let's do something like 100,000. This is clearly positive. So this is an absolute min. So the closest point is 1, 1. By the way, what's the distance? Yeah, I didn't ask that question, but what is it? No, because what you would do is you plug in X, this gives, S gives me, when I plug in 1, I get 1 plus -2 squared, so that's 5. But that's the square of it, so the actual distance should be square root of 5. Okay. That's the first one. Let's handle the second one. What is it, 0, 1/2? 0, 1/2 looks up very nice. So in this case, A is equal to 0, A is equal to 1/2. So my S in this case is X squared plus 1/2 squared, X squared minus 1/2. Plus X squared. But here's the important thing, the derivative. See what I have, B is 1/2. So this conveniently goes to 0, so this is 4x cubed. Minus, well, that's it. Right? Because B is 1/2, so that kills the coefficient of X. Right? So that's, and then A is 0, so that's. Ooh, even I can kind of get on this one, right? Let's see, to the left of this, you're negative. To the right of this, you're positive. So this is basically local, so absolute. Because it's the only critical number on the domain. Go down and hit that minimum, go up forever. It's got to be not just local, but absolute. Closest point. Zero, 0. So let's see what we've got so far. On this parabola here, I'm trying to put you. If you have 3, 0, closest point is 1, 1. At 0, 1/2, closest point was here. What about up here at 0, 1? Down a little curious. This one's a little bit more complicated. We have point 0, 1. Now you have A is 0, B is 1. Let's do this again. S is equal to X squared minus 1 squared. And then X squared. And the derivative, B is 1 and A is 0. That is going to be 4x cubed minus two X. And A is zero, so that's it. Well, this polynomial is also actually the hardest polynomial we've got, which is part A. This is two X times two X squared minus one. So now actually I get three critical. What do I get here? These three masses here. Let's see if we can figure out the sign. So what happens if you're way to the left of this? So what happens if you have a huge negative number? That's a positive and a negative, so it's negative. What happens if you've got an almost zero negative number? So very tiny. That's gonna be negative, that's negative, so it's positive. What happens if you have a t tiny, almost zero, positive, negative? And now what happens if you have a humongous number, billion, positive, positive? So now this distance that I'm measuring decreases, increases, decreases, increases. So, what happens here? Agree. What happens here? Here. Okay. Yes. How can zero? No. That you're thinking about a function. We're measuring the distance. Well, the square of the distance. So here's what happens, really. Well, so what are my candidates for absolute number? Right, it's got to occur here, because what happens, what this is telling me is far away. Now you're getting closer and closer and closer and closer and closer to the point. Now you're getting farther from the point. So after this, it's getting bigger. Now you're getting closer again, and now you're getting farther. So these are the only two places where you can have one of these two has to be where the local or where the absolute min is. So it's actually both of them, because if you plug in S either plus or minus one over radical two, notice how all the powers of X are even, so it flushes out the minus. This is actually plus or minus one over radical two squared minus one squared, plus or minus one over radical two squared, right? So it doesn't matter whether it's plus or minus, because this is an even function, it gets the same answer. So this is going to be a half minus one, which is minus a half squared. So I get 1/4, and then plus 1/2 is 3/4. And this occurs, these are both absolute. And does that make sense? Because look at the function. it should be x is 1 over radical 2 about 0.7, I guess. So about right here, if you will, that's where you get the minimum distance. And it should be symmetric, right? So what's good for the goose is good for the gander, right? So there should be two places for this particular function. Here's what happens. Up here, you're far away, you're getting closer, 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 closer. Okay, you're as close as possible. Now you're actually getting a little bit farther away. And now you're still pretty close, but you're as far away before you start getting closer again. And now you start moving farther away forever.
It's not short, it's just the distance.
That's exactly right. Well, it's the square of the distance. So what's the actual minimum distance? I didn't ask that question, but what's the minimum distance from the 0.01 to the parabola? The square root of this, radical 3 over 2 is the minimum distance. Okay, everybody understand? Okay, other questions? So on this exam tomorrow, is everybody able to, I hope make the review session this afternoon? Okay, good. A big focus of tomorrow will be, so we've covered, you know, a handful of sections. Optimization is going to be a big chunk of it, right? And I might ask you to max min some things. I might even ask kind of question in the previous exam, like what's the maximum function on a closed interval, because that's the same as this kind of question. Be able to do the linearizations, those kind of problems. Understand Newton's method. You need to understand, you need to know what the formula is, the x n plus 1 equals x n minus x n over convex n. Know that, but I really want you to understand what's going on with that, how it works, it's the tangent line, how it's successful. That's going to be the important thing, not plugging in numbers. And antiderivatives. How many of you have to take differential equations? Yeah, that's on the radar for a lot of you, I'm sure you major. So I'm going to give you, how many of you know what a differential equation is? Yeah, so we're all familiar with what an equation is. We use something like x squared plus 2x minus 5 equals 0. So a differential equation involves, it's an equation involving an unknown function in some of its derivatives, right? That's actually a very important differential equation. It shows up in an enormous number of physical problems involving heat, waves, electricity, etc. Can anybody think of a solution to this equation? Like, anybody think of an unknown function what's a solution to this equation? So I have a function, and when I add it to its second derivative, I get 0. So in other words, here's another way to think of this. It's a function that's equal to its own second derivative. Now there's a very quick smart aleck answer. I'm waiting for the smart aleck answer. Well, not quite, because e to the x is equal to, so e to the x would actually be a solution to this equation. There you go, cosine x, right? Because if you take two derivatives of cosine, what do you get? Cosine, negative sine, negative cosine. You think of another one. Sine also. This is why this equation comes up the way sine to cosine, right? The smart aleck answer that I was looking for was C, right? That's certainly was true. So differential equations comes up, and with a lot of you, this will be something that you have to look at later. And antiderivatives are very important to this, and you already know how to do some of this. So let me give you an example. I am thinking of a function, so y is f of x. And here's what I know. F prime of x is two x plus cosine x minus one squared plus one over x. X zero, and I also know that f of one is equal to I want to find this. So I've got some mysterious unknown function. What do I know about what the heck is trying to track down something? And I know that its derivative, it's two x, it's cosine x, minus one over one plus x squared plus one over x. And I know that f of one is okay, here we go, right? Because the mysterious function we're looking for should be an antiderivative of all this stuff. And so, yes, you're absolutely right. The antiderivative of two x was what? X squared? X. Is it minus sin x? It's actually sin. Here's a quick gut check. Right, let's look at these pieces as we go along. What's the derivative of x squared? Okay, so we got that right. What's the derivative of minus sin x? Minus, okay, so we're off a little bit, but we can fix this. How about this one? There you go. How about the one over x bit? Right. I usually say natural log of the absolute value of x, but here I don't really need to say it. Why do I not need to say it? Right, I'm only considering this x bigger than zero. Oh, x to the negative one. Oh, sure, you can do it that way too. Right. Well, so your formula blows up. So I think that if I interpret what you're saying, if you write it this way, if you try to do the antiderivative, you get x to the minus one plus one over minus one plus one, and you're like, uh-oh, that's a problem because I've got a zero in the denominator. So that's right, it's got to be log, doesn't it? Yep. We could do something like that. So let me address your question in just a second. I think I can do that. I'm not complete yet. What am I missing? And actually, this little piece of information right here will tell me exactly what the constant is. If I plug in f of one, I should get two, but I also should get what I've given plugged in here, which is one plus sine of one minus inverse tangent of one power of four, and log of one is zero plus c. And now I can solve for c by saying, well, like c is equal to one plus pi over four minus sine one. That's a crazy with the c, but it's constant nonetheless. So at the end of the day, my f of x here is equal to x squared plus sine x minus inverse tangent of x plus log x plus, I'll put this in parentheses, just in the self content, 1 plus pi over 4 minus sin. Okay, any questions? So. What's um, your own thoughts? Is this the kind of thing that you're curious about? Okay, so yeah, this is just two-step, right? I mean, here's what I know now. I know the second derivative looks like this. And I want to know the original function. Well, so we take a two-step back path. This was just like when we got the equations of motion for throwing a rock. F prime of x should be an antiderivative of this. So what's your favorite antiderivative? 6x. Cosine. I think it's sine x. And this is x to the minus 2 power, so I get minus x to the minus 1 over x. Plus constant. Now, I don't know what that constant is. This piece of information will tell me. So notice that f prime of 1 should be 0, and it also should be where I get my plug in 1 here. So it's 3 plus sine 1 minus 1. So C is minus 2 minus sine 1. Actually, instead of writing this every time, I'm just going to write C. But why not? And I'll provide it. So now, f of x is the antiderivative of 3x squared plus sine x minus 1 over x plus c. So let's see if we can figure out what that is. This is going to be What's your favorite antiderivative of 3x squared? Antiderivative sign is now it's negative. Antiderivative minus 1 over x is minus natural log x of 5. Antiderivative c is cx. And I'm going to get a new constant here, which I'll call k. Now, f of 1 is equal to 1, so this is last one here. My constant whatever. This is going to be 1 minus cosine 1 minus log 1. That's going to be 0 plus c plus k. So k is equal to 1 minus 1 plus cosine 1 minus c. 1 plus cosine 1. Cosine 1 minus c. So this column f of x is equal to x cubed minus cosine x minus natural log absolute value of x plus c, which is minus 2 minus sine 1 x, and my k, which is cosine 1 minus c plus sine 1 plus. There's my experience. Okay, any questions? Oh, right, the interval notation. No, well, so you want to do, no, you should be able to get an anti-grid, right? So you should be able to, when you do this symbol just means the anti-derivative. I mean, you could say the anti-derivative, but I mean, what's my problem? It's what I'm looking for, to find the anti-derivative. Okay, other questions? Okay, how about other questions about stuff we've done recently? Any old questions, quizzes, anything like that? Oh, okay. Which one was that? I could look that up. Oh, right, the cube, right. So here's the deal. I measure or find if the 28%. Error plus or minus 3/2. A estimate maximum error using 20-foot measurement. Probably would do. estimate relevant there. So hopefully everybody sees this problem. Measure this large cube. You got this cube and it's 20 feet. But maybe you only got a ruler that only like marks off every 3 inches or something like that. And so you've got this maximum error of like 1.5 inches, right? Half the, so you have these markers, so you'd be off by a half, 1.5 inches. Now, you really need to know the volume of this cube, right? I mean, this volume is, maybe you've got to put something in there, or maybe you've got to put it inside something, right? Maybe this cube sits at the bottom of like one of these aquariums, right? And you need to know how much water that's going to displace, right? Is it going to overflow the pool and make everything go everywhere? You need to know a good measurement of volume. So, oh, it's X. So my volume is equal to X. So I'm going to use this perhaps slightly off measurement to use volume, and I want to know how much I can screw it up. I want to estimate how much I can screw it up. Well, so what we're doing is we're estimating change in volume as X vary plus or minus 3/2 inch. So my measurement could be 20 feet minus 1.5 inches, or 20 feet plus 1.5 inches. I want to estimate how much that changes the volume that I've computed for this cube. What's one problem I'm going to deal with here? Yeah, that's right. Let's put this in feet. 3/2 inches times 12 inches 1 foot. It's got a unit fixing here. The inches cancel out in feet, so that's going to be 1/8. So 1.5 inches should be 1/8. Okay. Well, the idea is we want to use differentials to make our computations easy. Delta V is approximately equal to dV. Now, this is important. What is dV? I need to form, tell me what dV was relevant. dV for this here. 3x squared times what? So this is sloppy, but it's a good mnemonic device. Think of dV over dx as being 3x squared, right? And you're going to need this. Well, this is your arrow. So to make this work, I'm going to need numbers for both x and dx. What number should I be using for my x? 20 feet. And how about dx? 1/8 of a foot. Very good. So delta V, my approximate measurement of this, 3 times 20 feet squared times 1/8 foot. So that's going to be what? 1,200 over 8. So that's going to be about 15. I guess it could be plus or minus. So it looks like I could miss this by up to 150 cubic feet. Plus or minus. That's my answer. By the way, I really missed it by the full 3/2 inch. Is that an overestimate or an underestimate? Let's get to relative error. Well, the relative error is how much your volume changed divided by how big it is in the first place, right? Theoretical minus experimental divided by theoretical, right? Theoretical minus experimental is how much the total volume changes as you go from 20 feet plus or minus an inch and a half. That's your change in volume. Divided by the volume, your theoretical volume, which is what I get my measure 20. We use 20 to make this computation. Make this easy, I'm gonna do that. Because dB is much easier to use delta V. This is 3x squared dx over x cubed. So I don't have to put really numbers in until the last minute. 3dx over x. And let's see what do I get. This is going to be 3 times 1/8 over x is 20. So I get 3 over 160. So that's actually, that's less than a 2%. Now, my original, let's go back to that in this question. My plus or minus 150 cubic feet, is that an overestimate or an underestimate of the maximum area? What do you think? Well, actually, is it, if we take it on this, I thought you got it fixed. Because you told me you were gonna fix it up, what you looking for, and you came back. Well, I've been sure. Okay. So what do you guys think? Overestimate or underestimate? Well, let's see. What you're doing in these kind of problems is, no matter how you do this, captain differentials or whatever, what you're doing is using a tangent line to approximate, right? So if I were to graph this function, what I'm doing is I'm using 20 feet. I'm using the tangent line here to approximate this function, no matter whether I couch it in terms of differentials or couch it in terms of whatever I couch it. It's using this tangent line, this blue tangent line to approximate. So what do I get? Over or not? It's an underestimate, right? Because the blue tangent line hangs below the line. Blue tangent line is giving me this approximation information. In this case, because of the way the function is, it's actually giving me one small. So actually, my error could be a smidge bigger. Okay, any questions? All right, well, let's take the quiz for today, and I will see you folks, I hope, back here at 5 o'clock.